Right, well, welcome everyone to our fifth and in fact our penultimate session in this first series of Bite-Sized Corrosion. Now, over the past few weeks, we have tried to debunk the concept that corrosion is complicated and far too difficult for anyone to understand. And we've tried to achieve this by breaking it down into palatable, what we term bite-sized chunks, with the knowledge that every corrosion situation has an anode and a cathode present, and with the knowledge that only anodes corrode, we are now well on our way to getting to grips with the fact that cathodic protection transforms this corroding anodic structure into an inert cathode. And we can either use a sacrificial anode, something like magnesium or zinc, or an impressed current cathodic protection system. Last week, Neil discussed a variety of uses for impressed current CP systems, including such things as buried tanks, above ground storage tanks, the internal surfaces of a steel tank, some ships, and of course reinforced concrete, not forgetting buried pipelines. And with the risks associated with vandalism and the advent of high insulation value coatings, Neil noted that we can secure the CP stations at pipeline terminals. At the end of last week, Neil ended with a caution that stray currents can influence the selection of the ICCP location. So I think it now appropriate to ask Neil to please explain himself. Thanks, Neil.
We're going to have a look today at the challenges that stray currents bring to us. We saw right at the beginning when we alluded to the medical versions of the corrosion process that electrical interference is one of the systems that causes us to develop anodes and cathodes on pipelines and other structures. And the biggest cause that we have of electrical interference is railways. We looked last week at impressed current systems that are available for long pipelines. And as Vanessa mentioned, we've noted that you can locate an impressed current system inside the boundary fence of, say, in this case, a pump station, in order to secure it. What you may not have noted in this slide last week is that over here on the right-hand side, you can just see the masts of an electrified rail system. And electrified railways are perhaps the most significant cause of stray currents that we have. Internationally, in many countries, we have vast rail networks and vast pipeline networks, and both of these are in the ground. And so it is not exactly surprising that we do get some interference between the two systems. But not all rails are the cause of stray currents, and not all pipelines are susceptible to stray currents. So if you've got plastic pipes, you're in the pound seats in terms of electrical interference, because obviously there is no electrical interference with a plastic pipeline. So let's first have a look at some of the characteristics of the rail systems that are available around the world. And we're going to go through them in order of the extent of the rail system, and then after that we'll get into the technicalities. So perhaps the most widespread rail system that is around is the use of a catenary system, where the overhead wire provides the electric power, which returns through the rails, and it is powered by AC. Here is a typical example of an AC catenary system. This particular one is in Austria, and you can clearly see the pickup on the roof of the traction unit. In this case, it's a passenger train, and the return goes through the rail. The second most common is the use of direct current to drive the system, and also supplied through a catenary. So in parts of Europe, for example, you have direct current catenary systems. These are also present in Australia and in South Africa, in Spain, in Russia, in Holland, in Belgium. So they are quite widespread, although not nearly as widespread as the 25 kV AC systems. A lot of the earlier railway networks, particularly in southern England, and in this case, a metro system in Copenhagen, the power is supplied by a third rail. So over here, this rather strange looking device on the side of the rail is actually a pickup for the rail system, and the return current goes back through the rails. Some operators have taken this concept even further in that they have 4 rails. And if any of you have ever been to London and stood close to the edge of the underground, you will have seen something like this, where you have the 2 running rails for the trains, and you have 2 pickup rails for the power. These DC power systems are relatively low voltage, and as you can see, the systems are isolated from ground by these porcelain insulators, and so we get very little current that is discharged into the ground. And finally, believe it or not, we actually do have 3-phase catenary systems. Not very common, and particularly used in the mountain railways of Europe and also in South America. This particular photograph is from Switzerland, and you can see there are 2 overhead conductors, and the third conductor is the rail, and so we have 3-phase AC. So of these systems, which ones give us the problems? The main problem comes from anything where the DC return circuit is via the rail. And so our DC catenary systems and the DC 3-rail systems are the ones that are the biggest culprits in terms of giving us stray currents in the soil. There are some electrical theories, which are formal things which have been written, developed, proved by Kirchhoff, for example, and they can be summarized by this very simple equation that the sum of all currents at any one particular point is 0. In other words, current coming in has to go out. You cannot either accumulate or discharge current, except in something perhaps like a capacitor or an inductor, but that's only transitory. And the sum of voltages in a circuit is 0. So whatever voltage is applied, you're going to develop that voltage across the load. And the whole of our stray current analysis and intervention is based on these theories. So the current that is supplied by the traction system, in this case here you can see a traction substation, which is supplying power to a rail system, in this case a DC overhead catenary system. Whatever power is supplied by that traction system has to return to that same traction substation. So what are stray currents? Well, it depends on your point of view. If you are a facility owner suffering from stray currents, then stray currents are currents that are flowing in your structure, which do not originate from your own systems. If you are the generator of the stray currents, then a stray current is merely a current that goes through an unintended path. And fortunately, a lot of the operators who give rise to stray currents realize that this is a problem, and they take responsibility for endeavoring to mitigate the systems. So in this particular situation, which is a heavy haul DC traction system, we have 5 locos up at the front. Each loco is rated at something like 1 megawatt, and we have a total of something like 5,000 amps that is drawn through those rails. At 3 kV, 3 kilowatts, 3,000 volts, which is the operating voltage of the system, that is equivalent of 15 megawatts of power. That's a lot of power. So when that gets into the ground and travels through an unintended path, particularly in the form of a pipeline, we have some interesting challenges, such as this. This is a photograph taken of a pipeline which was buried, obviously, and it was coupled, not continuity bonded. And the line that you can see here was the edge of the coupling. And this corrosion has taken place because of stray currents that were in the soil, got picked up by the pipe, and then discharged back to soil on its way back to its original source, i.e. the traction substation. How fast does this occur? Well, if you use the conversion rate from current to consumption of steel, the approximate value is 10 kilograms of steel for every 1 ampere of DC for 1 year. It's actually slightly smaller than that, but we can use a figure of 10 to give us an idea of what happens. What does that mean? You can translate that into a corrosion rate. So if we had a current density on the surface of the steel of 100 microamps per square centimeter, then we would lose 1 millimeter of steel per year. Now, how on earth do you imagine what sort of current is 100 microamps? Well, a square centimeter is about the area of your fingernail. 3 milliamps is the current taken by an LED, an ordinary LED. So if you had the current needed to energize an LED flowing through a surface area the size of your fingernail, and that represents, for example, a defect on a pipe, the defect being in the coating system, then that current can perforate a 10 millimeter wall pipe in 4 months. That's scary. If we push it up to 1 amp, we can perforate a pipe in a matter of hours. So you can see that compensating for these stray currents is a really serious situation. How do we find these currents? Some people try and find them like this, but that's not really recommended. What we do is measure the potential of the pipe with respect to the ground. This photograph is just of a measurement that's taken on a pipeline where the pipe had been excavated to fix some coating defects. And these you can see over here. There's your typical coating defect, which is in the order of a square centimeter. If you have a look at the equivalent electrical circuit of a stray current situation, you can see that we have a number of circuits in parallel. Over here on the left-hand side, we have a traction substation, which is generating power. Doesn't matter whether it's AC or DC. That is transferred through the catenary system. It is used by the traction unit and returns through the rail. The rail has got some resistance. Because of that, we generate a positive potential in the track, and the track is in contact with the soil. And you can see here why it is the systems that have the return circuit in the track that we are most concerned about. So the current will travel from the rail into the soil, and some of it will just travel back through the soil and eventually get back to the traction substation. But over here we have a pipeline. Along the bottom, here's a pipeline, and that pipeline represents a parallel electrical path. And for those of you with some electrical background, you will remember from a long time ago when you did electrical circuits that current flows in every path of a parallel electrical circuit. And so we get current then that is flowing in this pipeline, and it also wants to return to the traction substation. So over here, the pipe is in contact with the soil, and the current returns through a contact where the coating is damaged. And we remember from our first discussion that when current leaves a surface, it is an anode, and we get corrosion. We can detect that by monitoring the potential of the structure with respect to soil. And this just gives you an indication of the changes in potential that can occur as a result of stray current interference from a rail line. This point over here is the quiescent period during the early hours of the morning when the trains do not run. And each one of these represents a passing train. What causes these electrical fields that we see on the rail? Well, firstly, the question of rail resistance. Depending on the type of rail that is used will determine the resistance of the rail. I mean, I'm talking about the longitudinal resistance, which is very, very small, but nevertheless, it still exists. Not all rails are welded all the way. And so we have bonds where there are joints in the rail. And these bonds represent relatively high resistance compared to the actual rail itself. So we need to make sure that the rail is adequately bonded when it is not welded. The third contributor to the electrical field is the tract of power. So if we have a heavy haul system drawing many megawatts of power, you're going to have a much higher field strength than a system which is perhaps only pulling a relatively lightweight suburban passenger train. How far apart are the traction substations? The further they are apart, the higher the voltage drop is going to be in the rail, and therefore we're going to have a corresponding higher electric field when the substations are far apart. You can tell where the substations are by the points where the power is fed into the catenary in this case, and these are located anything between half a kilometer and 30 kilometers apart, depending on the rail system. In between traction substations, we have track circuits. Over here, you can see a track circuit. This over here is a break between two adjacent power sources. And what happens with a break, when there's a break in an electric system, particularly if you're working with DC, you'll remember this short video clip from our first presentation. Just watch over here in the top left-hand corner as these four electrical units pass over a track circuit. 1, 2, 3, 4. The insulation of the rail from Earth plays a large part, particularly in light rail metro systems. The installation is actively insulated from the ground. So this is a photograph of a main line or a heavy haul line where the rails are mounted on insulating pads in order to try and prevent contact with the ground. However, this underlying ballast always provides some contact. This is an urban light rail system being installed, and here you can see that there is actually an electrical insulator placed around the rail in order to prevent the rail from coming into contact with the ground. And these are some of the control measures that are then used in order to prevent current from the rail getting into the ground. The current that goes or that is supplied by the substation has to return to the substation. So therefore, the characteristics of the earthing of that substation play a part in whether or not the stray current can return to the substation through the ground. If the negative of the substation is floating with respect to ground, then it will reduce the amount of current that tends to flow through the soil. Traction substations may be located many kilometers apart, and these substations are fed through overhead power lines. Over here you can see these power lines. We have had situations where the potential with respect to remote earth of two adjacent traction substations can be as much as 200 volts different, even though each one is nominally at ground potential. This does tend to play havoc with the signaling systems, never mind stray currents with pipelines. And finally, we said that AC systems hardly ever cause problems. This is true, but when there is the presence of highly mineralized soils, you can get soil rectification of the AC. And over here, you can actually see a ferruginous layer in the soil, which does tend to cause rectification of the AC that may be diverted via ground. And we've had situations where we have, in fact, picked up direct current interference from an AC source. So this current that then returns to the traction substation Most of it goes through the rail, fortunately. As we saw, it's thousands of amps. And when there are many rails in parallel, of course, the current is shared between the various rails. However, when there is a pipeline in the ground in the vicinity, some of that return current picks up the pipeline and follows the pipeline. But what happens if that pipeline doesn't necessarily go back to the same location as the traction substation? Maybe it goes via somebody else's pipeline. So here you can see a situation where we have a number of different pipelines which are also interacting with the rail system. And so you can get stray currents that jump from pipeline to pipeline. The currents can also go through geographical features. So for example, if we have got wetlands or rivers, these can also conduct current or provide a preferential path for current in the soil. We've known about stray currents for many years. In South Africa, the original Durban-Joburg lines were installed in the 1960s, was the start of the challenge in South Africa, because the construction company found that the line was already full of holes when they came to pressure test it about 3 months after installing it. In the 1980s, a pipeline was laid in a remote area where everybody thought, oh, well, the resistivity is high, there are no railways around, we don't need to worry. When they came to commission the pipeline 2 years later, it was perforated. So this is that particular situation. Over here, the blue is the pipeline. The red in the top left-hand corner is the railway line. And we had stray currents that traveled through the pipeline from the dam to a wetland. And that current then returned down this preferential path to a point over here. And we had corrosion of the pipe at that point. So you can see that it is very unwise to assume that you do not have stray current interference because you are nowhere close to a railway line. Close is a relative term. We have stray current circuits that operate over hundreds of kilometers. Pipelines are not the only things that suffer from stray currents. Steel decks built over rail systems can also be affected by stray currents. In this case, the stray current affected the foundations of these columns. Bridges built over railway lines can also pick up and discharge stray currents. In this particular case, the stray current value was something like 40 amps. Railways are also not the only cause of stray currents. We saw that we have an impressed current system on a pipeline where there is a potential gradient, in other words, a field set up by the anode, which is the positive electrode of this cell. If we now install a second pipeline, we land up with an interference situation where the second pipeline passes through the voltage gradient of the anode and suffers from interference in this area over here where it crosses the protected pipeline. And this situation happens all too frequently with the increased density of pipeline networks, never mind whether you're in South Africa or anywhere else in the world. Those of you who live in the Northern Hemisphere may well be familiar with this site. The aurora borealis is caused by the geomagnetic interaction between the sun and the earth. And this sets up magnetic fields as a result of the solar wind that is passing past the earth. This in turn causes what we call telluric currents in pipelines. And these currents can occur particularly in pipelines that run from inland towards the coast. These are like stray currents, but the problem is that they don't fluctuate rapidly. They change on a 24-hour cycle, depending on the angle of rotation of the Earth. So now we know something about the source of these stray currents. How do we control them? At one stage, it was thought that all you needed to do was isolate the pipe 30 meters each side of a rail crossing. And here is a photograph where there's an insulating flange kit that has been installed in the pipeline. And the concept was that the potential or the voltage from the rail would then not get into the pipe. The problem is that the electric field associated with the rail is way, way bigger than 30 meters. 30 meters just happens to be the width of the servitude of the rail system. So we need to do something more than that. There are a number of ways of controlling stray currents. Perhaps the most important aspect of all of them is the location of the stray current control system. And we can use NDUs and FDUs and TRUs and RMUs and you name it, we can do it. But that is next week's exciting episode where we will translate or decrypt these wonderful acronyms. Think about this. A cathodic protection system typically has a power of 1 kilowatt or less. Some of them may be a bit bigger. The traction system in the rail is 15 megawatts. I'll leave you with that question.
Thank you, Neil. Stray currents are both complex and challenging, and it's helpful to grasp their complexities a little better. As a control freak, there's a lot that we don't have control over, and I guess it's good to try and control what we can. So right now, I'm going to choose Team David. After that discussion, there are a couple of questions, I think. The first question today is a reiteration of what was raised a few weeks ago when we looked at sacrificial anodes. And the question is quite simple. Can we use sacrificial anodes in a stray current situation?
Well, if I'm allowed to use a good South Africanism, the answer is ja, nee. It depends very much on the intensity of the stray currents. Firstly, the voltage, the driving voltage of a sacrificial anode system is very low. As we saw, it's only magnesium is 1.5 volts with respect to soil. And a traction system stray current voltage can be many volts. The relationship between voltage, current, and resistance comes into play, and the net result is that the traction interference voltage may well be greater than the driving voltage of the sacrificial anodes, in which case the sacrificial anodes may not be able to cope with interference. But sacrificial anodes are often used to mitigate interference between pipelines, for example. The other challenge with sacrificial anodes is that if they are in an area where there is stray current pickup, the anodes actually act as a stray current pickup point, which can intensify the stray current magnitude in the pipelines. And that, of course, is something we don't want to happen. So there isn't a simple answer to your question, and the situation has to be evaluated on its merits.
Thanks, Neil. I guess we can't make a quick and easy one-size-fits-all answer or solution, and we really need to look at each possible scenario on its own merits. And like a true property purveyor, location is really the key thing with stray currents. I think you've given us some food for thought, and thank you for that. And really thank you to everyone for joining us for lunch today. And just a reminder, please to join us next week for our final session in this summer series of Bite-Sized Corrosion Conversations. And we'll be looking, as Neil alluded, to some of the plant and equipment that we use to protect pipelines and solve our problems. So we look forward to seeing you then, and thank you all for joining us. Have a great day.